Memoization in dynamic programming. Memoization is an optimization technique used in dynamic programming to store the results of expensive function calls and reuse them whenever the same input occurs again. This way, redundant calculations can be avoided. When we learned about dynamic programming, we learned that storage mechanism is the core of dynamic programming. Why is it? It is because storing intermediate results is what makes dynamic programming different from all other algorithmic paradigms. Coming to storage mechanisms used in dynamic programming, you generally use two major storage mechanisms. One is called memoization and the other is called tabulation. Memoization is a top-down approach for storage, while tabulation is a bottom-up approach for storage. From this itself, you would have understood that memoization is used whenever you use recursion and tabulation is used whenever you use iteration. Why is this? Because recursion is always a top-down approach. That is, if you want to solve any problem using recursion, how will you solve? Recursion will start from the top and then you will keep making recursive function calls downwards so that you can find a solution for the problem. But in case of iteration, you will be building it bottom up. So whenever you want to solve a dynamic programming problem using recursion, that is when you use memoization as the storage mechanism. And whenever you are using iteration to solve a dynamic programming problem, that is when you use tabulation as the storage mechanism. In this lecture, we are going to learn about memoization. We are going to focus on memoization. So memoization, we already understood it is used whenever you use recursion. Whenever a sub-problem is solved during recursion, for the first time, what will you do? You will store the result in a data structure. Why is this called as memoization? Do not confuse this with memorization. This is memoization. The reason it is called memoization is that it is derived from the word memo. Memo will be a word very familiar to you. What is a memo? Memo is a note, or you can say a record that is made for future reference. When will you make a memo? Let us say you are learning this. You will make a memo and write few points so that you can refer to this in future. If you want to refer back, you can refer to the memo you have written and again remember whatever you had learned. The same purpose is what memo is used here. So whenever you want to take a note for future reference, that is called as memo. What about the suffix ization? Ization, this indicates the process of making or doing something. This is called ization. So what is memoization? Memoization is the process of making a memo. That is why you call it as memoization. So what is this process of memoization? You are creating a memo of the results of function calls, that is for specific inputs, so that whenever the same function call is repeated at a later stage, what will you do? You will simply retrieve the stored result and directly use it instead of recomputing. So let us understand this with an example. That will be easier. With an example, we'll easily understand what is the improvement that memoization will bring into a normal recursive approach. What we'll do is, we'll try to see what is the recursive approach for a problem, and then we'll see how memoization is going to improve that approach. Okay, we'll take the same example that we used in DP lecture, which was of Fibonacci series. So Fibonacci series goes like this: 0, 1, 1 and so on. So first two numbers in Fibonacci series, those are fixed. That is, f of 0 is 0, f of 1 is 1. After that, if you want to find any Fibonacci number, it is found as the sum of the previous two Fibonacci numbers. That is, f of n is equal to f of n minus 1 plus f of n minus 2. This is how you find Fibonacci series. So after 0 and 1, which is the next Fibonacci number, it will be 0 plus 1, which is 1. Next one will be 1 plus 1, which is 2. Next is 1 plus 2, which is 3. Next is 2 plus 3, which is 5, and so on. So if you want to write a recursive solution for this problem, that is for finding nth Fibonacci number, how will you do this? Let us say you want to find f of 4. You have to make two calls. One is to f of 3 and the other is to f of 2. Similarly, for f of 3, you will again make calls to f of 2 and f of 1. This f of 2, again you have to make calls to f of 1 and f of 0. This f of 2, again f of 1 and f of 0. This is how you make recursive calls for finding Fibonacci series. Let us try to write this in a function and then we'll see how memoization will improve this. Okay. So let us say you want to find nth Fibonacci number. So we'll call it as fib of n. This is the function. How will you write this function? For this, first step is to see whether it is the first two Fibonacci numbers, that is f of 0 and f of 1 are 0 and 1 respectively. So you don't do any computation. That is, if let us say your n is less than or equal to 1, in this case what will you do? You will simply return n. Why are you returning n? Because f of 0 is 0, f of 1 is 1. If it is larger than n, that is if it is not this case, then what will you do? You will return Fibonacci of n minus 1 plus Fibonacci of n minus 2. This is what you are going to do. This is your normal recursive solution. What is the problem with this solution? Here I intentionally left a space so that we'll fill it using memoization. So this is the function. In this function, what is the problem here? This surely is going to solve the problem. That is, it will make all these recursive calls and it will find you the right answer. No doubts on that. But the problem is, it is going to make a lot of repetitive calls. See how many repetitive calls it is making. All these are calls to f of 1. Here it is calling f of 0. Here also it is calling f of 0. Here it is calling f of 2. Here also it is calling f of 2. So these repetitive calls, they'll grow exponentially as the number n increases. And what will happen? It will make your time complexity order of 2 power n. So what is the problem with this 2 power n time complexity? This means when your input size increases, your time taken to run the algorithm is going to increase exponentially, which means in all practical purposes, this particular algorithm becomes very inefficient, because generally you use an algorithm if you want to compute it for larger numbers. Otherwise, you will directly compute. Whenever you want to find it for larger numbers, time complexity becomes order of 2 power n, which is exponential time complexity, which means your algorithm is going to take a lot of time to run. What are you going to do with memoization? Let us see the change that can be brought with memoization. In memoization, before going into all these steps, you will add an additional step. What is the additional step? Additional step is if your n is found in memo. Let us say you have a memo, and in this memo, if you already can find n, the number, then you should directly return m of n. That is, whatever be that n that you're finding from memo, you should directly return without doing any of these computations. And one more thing, you have to keep filling the memo. So if this is not the case, you should add one more line here. That is, once you are computing, whenever you are computing, you should add it in the memo. That is, m of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. So whenever you are computing anything, you are always storing it in the memo and you will return whatever is present in memo, right? M of n. What will you do now? Here the speciality is, whenever you are computing anything, you are storing it in memo, and whenever it is available in memo, you are not computing, you are directly using that result. What happens now? This time, this part of complete function call is not required at all because f of 2 is already calculated here. So when you check memo here, you will understand that you already have the value of f of 2, because of which you don't have to compute and you can directly fetch from your memo. This is how memoization is going to improve your time complexity. Any of the function call which is made for the second time, that will be directly computed using the memo. What happens then? I am saying you that every function call is computed only once. Whenever you are making second call, you are directly fetching, which means any function call is computed only once, which means total function calls should be order of n. So your time complexity decreases drastically from order of 2 power n to order of n. So this is what memoization brings in. Your simple recursive solution that would have made order of 2 power n function calls, and your time complexity of the algorithm, that is whatever I wrote initially, the recursive one, that would have been order of 2 power n. This is also recursive, but this is using memoization. With memoization, we improved this time complexity to order of n. This is where memoization is useful. When should you use this? Whenever you see overlapping subproblems and optimal substructure. This is what we already discussed in DP lecture, that these two conditions should be satisfied whenever you want to solve a problem using DP, dynamic programming. Optimal substructure and overlapping subproblems. And what are the limitations of this memoization technique? The limitations are, one is space complexity. You are going to store the results of every single computation, which means it is going to take up your space. So space complexity will increase whenever you use memoization. And secondly, as we said previously, it is not always applicable. It is applicable only when certain conditions are satisfied. That is, overlapping subproblems and optimal substructure are satisfied. The only thing you have to be concerned here is about space complexity. So in order to improve on the space complexity, we'll try to use tabulation instead of memoization. Let us see if that will improve anything in the next lecture.